Hi, ladies and gents. This time we're going to talk a little bit about springs. We're going to refer to spring potential energy, and we're going to talk a little bit about Hooke's law. Here goes. Energy can be actually stored in some sort of a coiled spring or a rubber band or material that's under some sort of a stretch. You've all done this. You've taken a rubber band and you've pulled on it, and you've got energy stored into it because of its position, and any sort of position stored energy is potential. But you've also probably done this. Old-fashioned watches, not battery-operated watches, but old-fashioned watches, you would wind the battery, and you would wind the watch. And inside that watch, there was a little spring, and you would store energy in that coiled spring, and the energy would be given back as the watch wound. Same sort of thing works for a music box. In a music box, there is a spring that you coil up as you add energy to it by winding it up, and that uncoiling actually runs the music box. This energy can be stored in lots of different things, everything from collapsing the springs on your car to your garage door springs. So we're going to talk about how do you calculate and mathematically deal with this spring potential energy. Before we do that, we have to talk a little bit about something referred to as Hooke's law. This is Hooke's law, another equation that I would definitely copy down, put on your formula sheet, where F is the force that is applied to some sort of a spring or an elastic material. X is the displacement from the rest position. Now, what do I mean by rest position? If I have a spring that is like this, and I stretch it to go to this is going to be my change in length or my displacement from its rest position, and that's going to be my X. Same thing can occur for compressing a spring. If I have a spring like this, and I compress it down to this is going to be the X that I'm going to deal with in a particular situation. K is something referred to as the spring constant. The spring's constant is going to be a factor of very, very unique number for each material. So if you've got a rubber band, the qualities, the properties of the rubber band, the kind of spring you have, its diameter, the thickness of the steel it's made out of, spring constants are very unique for each stretchy material. Now, Hooke's law was produced by Sir Robert Hooke, and Sir Robert Hooke was not quite 10 years older than Sir Isaac Newton, and in many ways, Hooke was Newton's nemesis. Sir Robert Hooke was president of something referred to as the Royal Society, which was a group of scientists who met in London every few months back in the 1700s for the purpose of actually exchanging intellectual ideas. Well, Newton was this shy, bookish young man, and at one point in time, he made a presentation before the Royal Society, and when Newton got up and made his presentation, Hooke accused Newton of plagiarism, because Hooke had actually started to work on the inverse squared law of gravity, but he never quite figured it out. And the reason he didn't quite figure it out is Hooke didn't invent calculus like Newton invented calculus. And because Hooke never really figured this out, but he had worked on it, when Newton got up and said, "Oh, I think I've got A, B, and C figured out," Hooke just said, "You are a big lying plagiarist." Newton was this tender, shy character, and he went home and basically didn't tell anybody about his discoveries for years and years and years and years. Eventually, he published his work on motion and gravity, and when he did that, through time, he rose himself to be president of the Royal Society. Now, when Newton became president of the Royal Society, he did his darndest to eliminate all traces of Sir Robert Hooke from the writings and the paintings on the wall and anything that contained Hooke. So what this proves is it doesn't matter how big a genius you are, you can still be petty, which is one of the biggest rivalries ever recorded in science. Hooke's law says this: if you have a spring, the bigger the force you apply, the further it stretches. Now, this is not a terribly profound concept, but it is a nice, easy mathematical idea. So if I apply one quantity of force, the spring is going to stretch so far. If I double the force, it's going to double the elongation. If I had 3 times the force applied, it will go down to the point of having 3 times the elongation. It's a nice, beautiful linear relationship. And labs typically are done in most physics classes to actually deal with Hooke's law, where you have a spring, you put a force on the spring, and you measure the extension, that change in length. And this works beautifully. You usually get a nice straight line graph, and the slope of that straight line graph is going to be your spring constant. And this works beautifully until you hit something which is called the elastic limit. And the elastic limit is when you stretch a spring to the point where it won't stretch back. I don't know about you, but if you take the little tiny springs that are in maybe like a ballpoint pen and you really pull on them with a large quantity of force, you can take that spring and get it to look something like that, and it's not going to stretch back. So as long as you maintain the integrity of the spring and don't exceed this elastic limit, get a beautiful linear relationship. Now, because of the fact that coiled springs can hold energy, we can calculate what is referred to as spring potential energy. Some places you're going to see EPE for elastic potential energy. Again, totally depends on the author of your textbook. This is going to be 1/2 K. K is our spring constant, very unique for each spring, and X is the amount of stretch. So what can be done is you can compress a spring, give it some stored spring potential energy, and then when you let that go, bing, it can give kinetic energy to whatever is attached to it, or it can also do work against things like gravity or friction. We're going to do an example problem next. See you then.